The cover says Advanced Calculus, but this is not the usual course in partial derivatives and multiple integrals. It is by Loomis and Sternberg, both of the Harvard Mathematics Department, and it grew out of an honors course they gave in the 1960s. The preface states the prerequisites plainly. You need one variable calculus from a rigorous point of view, some linear algebra, comfort with limit and continuity arguments, and a little experience with partial derivatives. It suggests Courant, Apostol, Spivak and Hardy. The book divides roughly in half. The first half develops the calculus entirely in the setting of normed vector spaces. The second half deals with the calculus of differentiable manifolds. The structure of the space comes first, and doing calculus on it comes second. Here is the central shift. In elementary calculus, the derivative is a number, the slope of the tangent line. Here the differential is a linear map, the one linear approximation closest to the actual change, and the gap between them is of smaller order than the displacement. Chapters 0 through 2 are algebraic preparation. Chapter 0 covers logic, quantifiers, and sets, and the authors say it is mainly there to be referred back to. Chapters 1 and 2 build vector spaces, the dual space, matrices, trace, and determinant. Chapter 3 is the heart of the first half, the differential calculus itself. It starts from norms and continuity, passes through infinitesimals, the differential, directional derivatives, and the mean value theorem, and reaches the implicit function theorem. Chapter 4 lays the analytic groundwork, metric spaces, compactness, completeness, and the contraction mapping fixed-point theorem. Chapter 5 treats scalar product spaces, and Chapter 6 turns those tools on differential equations and Fourier series. Chapter 7 is multilinear algebra, with alternating tensors, the determinant, and the exterior algebra. The authors call it a reference chapter. Chapter 8 builds the axiomatic theory of Riemann integration, including the change of variables formula. Chapters 9 through 11 carry the second half, manifolds, the tangent space, vector fields and Lie derivatives, then integration on manifolds and the divergence theorem, and finally exterior calculus and Stokes' theorem. The preface warns that Chapter 9 is the hardest. Chapters 12 and 13 are independent of each other and serve as illustrative applications. The first is potential theory, with Green's formulas, the Poisson integral, and Dirichlet's problem. The second redoes classical mechanics, using symplectic geometry. This series follows the book in order, at roughly 2 to 4 printed pages per episode, and it does not skip the start advanced sections. That comes to about 169 episodes. The next one starts at Chapter 0, with logic and quantifiers.